It's an image data set. So computer vision is one of the most important parts in the deep learning dream, which aims to enable machines to see just by mimicking the biological human vision system. And today, deep learning computer vision is allowing autonomous drones, self-driving cars, and robotic systems to analyze, process, and understand the content of digital images and videos quite through cameras, so that they can decide how to act. For example, in self-driving cars, should I turn left, should I turn right, should even I hit that person? So, computer vision is used for a wide range of applications. Among these applications we have self-driving cars and autonomous drones, robotic surgery, and many other medical applications. We have intelligent surveillance in shop stores, streets, etc. We can do art creation using style transfer and improve the quality of our images inside our smartphone, for example, and also to have some fun using social media applications like Snapchat and Instagram. So one of the most important questions is that in the computer vision is what objects are in the scene and where these objects are located. And this is called object detection, which is a core task for each one of the previously mentioned computer vision applications. So in recent years, object detection has made great progress along with the development of deep learning and new algorithms proposed. However, the most current object detection methods require powerful resources. So now how to train a computer. For human, it's obviously in this image it's a cat, but for a computer it's a very hard task. So because all the computer sees is a big matrix of numbers. So to train the computer, we need firstly to show him thousands of images that contain our objects of interest that we want to detect. And after the training process, the computer will be able to distinguish between the different objects in the image. There are many methods to train the computer to see, and previously we used traditional machine learning algorithms where we needed to apply hand engineered algorithms to extract features from the image. However, recently CNN, which stands for Convolutional Neural Network, is an end-to-end model that gives us the possibility to skip the feature extraction step, which is automatically learned from the training process. So CNN is one of the most powerful computer vision algorithms, and it is the state of the art for object detection. It is basically layers of convolutions followed by pooling and fully connected layers, where the convolution and pooling layers are used to extract features from the image. However, the fully connected layers work as a classifier. So there are two cases for deep learning based object detection. In the first case, we need high-performance computers equipped with powerful GPUs in order to execute these algorithms. However, in the second case, we need to implement these algorithms inside the machine itself, which is based on embedded systems, small devices, with limited hardware resources. In the first case, we take the example of drones. The drones collect data through its cameras and sensors and transmit them to the on-ground workstation in order for analysis of these images. This gives to drones the ability to save power by offloading compute-intensive operations, a high detection accuracy thanks to deep convolutional neural network, and a high speed of analysis for real-time object detection. However, the wireless transmission takes a long time in sending the collected data, which means an additional cost added to the latency of the system. And also we have some security issues. Several deep CNN-based object detection algorithms were recently proposed. Their performance depends on the ways where they are used. We can divide object detection algorithms into two categories. The first category is the two-stage algorithms, where it's mainly include the RCNN family, where in the first stage we need to generate region proposals, and in the second case is to classify them into different classes. but the problem with these techniques is are very slow and not suitable for neither real-time object detection or small devices. In this second case, or second category, we have the one-stage algorithms like SSD and YOLO. YOLO see for you only look once. And the idea behind these algorithms is to run the entire image in the CNN at a single pass. The deep CNN-based models have achieved great accuracy on object detection, as shown in this table. However, these models involve a large number of parameters to be trained, and which make it computationally very exhausting, especially in the field of embedded systems. From the perspective of timing performance, one-stage algorithms achieve real-time results in detection. However, the accuracy rate are not as high as the two-stage algorithms. Recently, YOLO has been improved with its two versions, YOLO version 2 and version 3, which are faster, more accurate, and can detect a large number of classes. All the previously discussed object detection algorithms are based on deep CNN with a large number of layers, filters, and parameters to be trained. And these are the most known CNN architectures. We have AlexNet, which is the entry, considered as the entry to image recognition, with 8 layers. VGNet with 16 layers. We have a large number of parameters to be trained, 138 million parameters. GoogleNet, which is the winner of the ImageNet competition in 2014, it achieves only 6.8 million parameters thanks to the inception module. And ResNet is another deep learning, deep CNN architecture. We can achieve 152 layers to be trained using the skip connection. In real-world application, we need to implement the object detection algorithms inside the machine itself, which is based on small devices, embedded systems, with limited hardware resources. So embedded systems have limited resources not only in computation power, but also in memory, which make the majority of current object detection algorithms not suitable for small devices. In order to run object detection algorithms fast enough on small devices, we need we don't use those off-the-shelf algorithms, CNN architectures. Instead, we use a lightweight CNN versions, like shown in this table. These are the most powerful lightweight CNNs, like SqueezeNet, MobileNet, and PeleNet. So the lightweight CNN versions improve the power consumption, the battery life, the flight time for drones, or operation time for other robots. Low power computing systems can reduce thermal problems and cooling requirement, which is very important in the drone field. These are some object detection models based on lightweight CNN architectures with less layers, filters, and parameters to be trained than the original works. And these models achieve high accuracy and speed for even small devices. All these results are based on NVIDIA Jetson TX2. As conclusion, so small devices need accurate and fast object detection methods that are suitable for its low power and low processing. Lightweight CNN architectures give us the possibility to execute these accurate algorithms on limited hardware resources. As a future work, we are now working in a new project since only a few months. So we want to train different lightweight models on our own data set and develop new models in order to implement on an STM32 based flight controllers. So as we've shown here, I'm just a beginner in this field. I worked only 3 or 4 months on these subjects. Where I'm working now, they are developed the drones, fixed wings, and multi-rotors in surveillance and agriculture field. So now we want to implement the artificial intelligence inside these drones to make them autonomous. And thank you for your attention.